Hello. So in this video, in this final chapter for integration, we're going to look at areas under curves, but when we add straight lines into the mix, so it makes things a bit more complicated. Okay, so before we look at examples, well, actually, let me just consider a straight line, right? So what I'm going to draw as an example is the straight line here, right? And I'm going to call that y is x minus 5, let's say, right? So 5 will be there, okay? The root, right, where it intersects the x-axis. There, 5. So what I'm going to ask first is, if I want to find the area between x is 5, and let's say here when x is 10, let's say, right? What would the area be? So if I do it in red, how would I find the area here between 5 and 10? How would I find the area? So area is, well, what is the area? And hopefully you can visualize that we've got a triangle, right? So one approach we could find the area, method 1, is triangle, right? And in particular we've got this triangle here, well, here, right? A triangle here, where obviously we've got 5 here, then 10. So then we know the area of a triangle is a half base times height. Well, we know the base here, that's 5 across, that's 5, right? The base from 5 to 10, the difference is 5. Well, what about the height? We don't know how to get to that, right? Well, what we are given is the equation of the line, so we can find that point there, the y coordinate, right? When x is 10. How are we going to find that then? Well, actually, we can sub x is 10 in, so I'm going to say, if x is 10, then y is going to be x minus 5, so it's 10 minus 5, which is just 5. So the coordinate here then, that's going to be x is 10, y is 5, right? So we've got the coordinate. Okay, so now we know what the height is, right? The height is how far up in the y direction we've gone, right? So here y is 0 at the base, and here y is 5. So actually how far we go up is 5 across, right? So now we've got a height which is also 5, okay? So then we got our area, so therefore our area is a half times base of 5 times the height of 5. That'll be 25 over 2, okay? And that's my area. Cool. So we can visualize, we can use triangles to work out areas under straight lines, okay? But actually, if we're dealing with areas under a straight line, well, a straight line is still a curve, really. Obviously, it's not curved in the I guess in the sense of like a quadratic curve or anything like that, but it's still like a function that we graph, right? We got a graph. So actually, we could also alternatively use integration to do the area under the curve between these two limits at 5 and 10, okay? So then the area would simply be integrating between 5 and 10 of the line which is x minus 5 dx, and then we just integrate that, right? So x would go to x squared over 2, or half x squared, and minus 5, when we just add an x on, so minus 5x between 10 and 5. So then if we sub our limits in, we'll get a half of 10 squared minus 5 lots of 10, take away a half lots of 5 squared, take away 5 lots of 5. And so if we put all that in the calculator, hopefully we get 25 over 2. we do indeed. We do get 25 over 2. That's great, right? So we've got two different ways of approaching these problems where we want to find an area under a line. Okay, we can construct a triangle and then work out the base and height, and then obviously do half base times height. Or we could integrate. Okay, integrating is, I think, the safer option. You don't have to faff about with finding heights or coordinates or anything like that. As long as you know obviously where you integrate between, you can integrate it, but it might be a bit longer. But it's a safer way, especially when you see more complicated problems. It might be hard to visualise what shape you need to make or the triangle you need to you get. Okay, but we unlock with integration an alternative way of finding the area in this case. Okay, so don't forget, because it's not a curve, it's still a graph. We can still integrate to find the area underneath, just like any other curve we've seen so far. Okay, okay, so with that in mind, we're going to see now why that was important to go over, because we've got this example here and we've got a straight line and a curve. This curve is y is x of 4 minus x, with the line y is equal to x. Okay, you can see the area in yellow here, it's between the curve and the line. So it's not straightforward as just integrating the curve, because if we integrated just the curve, it would be the whole area underneath the curve, right? So it would look a bit like this. We'd have this extra area as well, but we just want the area in yellow, which is between the line and the curve. So it's a bit more complicated. Okay, so, well, first of all, we need to determine the limits, right? Where is the area, where's the region between? Well, firstly, it's between 0, great, the origin, but then it ends at this point here, which is the intersection point. We don't know what value of x that is, right? But we can find it, right? Because isn't that just an intersection between the line and the curve? The curve and line intersect. So we're going to find that intersection point. So that means y is equal to x, which is the line, and y is equal to x of 4 minus x, which is my curve, okay? So what I can do here to find intersection, well, it's just two graphs intersecting. We saw this before. It's just simultaneous equations. We can equate them together to so then the y's would be the same. So in a way, we could get that x is x of 4 minus x, and then we could just solve for x, right? Okay. So then if we expand that, we get x is 4x minus x squared. Then if we add everything to one side, we get x squared. Take away 3x equals 0. And so if we can factorise to get x of x minus 3 equals 0, so then x equals 0, or x is equal to 3. Well, obviously we know that intersect at 0, we've got that already, but then 3 must be this x value there, the intersection point. So we are integrating between 0 and 3. But what exactly are we integrating? Well, we're not just integrating the curve, because we've got this line to deal with as well. Well, to help visualise what's going on, well, let me draw the graph again. But I'm going to draw just the curve for now, right? There we are. So obviously we know that's 4 there, 0 there, but we're between 3, right? So something like that, right? So x is 3 and 0. Well, the area under the curve, well, it would just simply be this whole area here, right? Under the curve between 0 and 3. But obviously we don't just have the curve, so then now let's add on our line. If I draw another graph, so I have my curve, again between 3 and 0, but I also have the straight line, right? I have the straight line, like as so, right? So what's happening is, this red area as a whole is being split up now because of this line. I have the yellow area, but I also have the blue area, right? So the way I can work out my the yellow area, well, if I consider the area of the the whole area under the curve. So the area in yellow, that's going to be the area in red here, right? The area under the curve in red. But as we saw, the area in red, which is blue and yellow combined, right? You can see here in the second diagram, the area in red is the same as the area in yellow and blue, right? Which is split up above and below the line. Well, then actually, if we want the yellow part, then we take away the area in blue. Okay? So hopefully you can visualise that. And so then, to be a bit more specific then, the area in yellow, in terms of the curve and the line, well, the area in red is just the area under the curve, right? And then I'm going to take away the area in blue. Well, actually, hopefully you recognise the area in blue is just under the straight line. So it's area under line. Under the line, right? So basically what we need to do is essentially then work out these two quantities here. The area under the curve and area under the line. Well, actually, we do have the tools to work that out, okay? Well, firstly, the area under the curve... This is under the curve. That's the curve here, right? The area in red, right? The area just under the curve as a whole. So this whole area here in there. Well, if we look at my diagram, the red diagram here, the area is just simply the integral between 0 and 3, right? Of the curve, and the curve has the equation, if you remember. X 4 minus x, right? Dx. Okay. And so then if we integrate that, well, that'll be... Well, actually, no, we can't integrate it, can we? Because we need to expand the brackets. Can't integrate it as it is. So if we expand that, we get at 4x take away x squared dx. And... so then we can integrate. Well, 4x will go to 4x squared over 2. Then take away x squared. That will go to x cubed over 3 between 3 and 0. We can actually tidy these fractions up a little bit. Because 4 over 2 here goes to 2. So we have 2x squared. Take away a third x cubed between 3 and 0. Now we plug in our limits. So we have 2 lots of 3 squared, take away a third, lots of 3 cubed, then sub in 0, we get 2 lots of 0 squared, take away a third, lots of 0 cubed. So if I work that out, I actually just get 9, okay? That's the area under the curve, right? Now we need to work out the area under the line, the area in blue here, right? So if I write that down, area under line, which is blue, okay, and the area under the curve was red. Okay, so the area under the line, under the straight line here. So if we look at our yellow and blue diagram here, I hopefully spot the area in blue. If I really do, if I highlight the edge, if I highlight what, a bit thicker than that. So if I highlight the outside bit of the region in blue, hopefully you recognise we've got a triangle, right? We got this. We got this triangle here. The area which is blue. And okay, so we got that area then. We got that triangle. Hopefully you can see that right. I've drawn it right, the triangle. So we want the area of the triangle, right, the area underneath the line. So it's a triangle, so the base, well, it's between 0 and 3 on the x-axis, so the base is 3, right? What about the height? The height up here. Well, we don't know the height, we don't know the coordinate up here, so I'm going to get rid of this blue. Oh dear. Let me draw the axis again. So I'll get rid of that now. But I don't know the height, right, of the triangle. But I need to find that coordinate. There, right? Because then if I know I know when x is 3 on the x-axis, but what about up here? What's the height? How far has it gone up? Well, actually, that point is what we worked out. That's the intersection point, right? We saw that the intersection point x is 3, so the x coordinate's 3 here, but the y coordinate then, well, actually, if we sub x is 3 into either equation, well, y is equal to x, right? So y is equal to x, that means y would be 3 as well. So actually, we're in this situation where we've gone up by 3, right? So the height is 3. If that makes any sense? Again, as a reminder, because this is when x is 3 and y is 0, and then up here is when x is 3, y is 3. So we've gone up by 3 y units, okay? Hopefully you can see that. That's why the height is 3. So we calculate the y value at the point above, right? So that gives me a height of 3. Well, actually, we're now in a position where the base and the height is 3. So therefore, the area is a half times base times height. That means it's a half times 9 times 9. That is 9 over 2. So that is the area of the triangle, which is the area under the line, which is blue. That's the blue area then, right? The blue area, which is in the triangle that we just saw. Okay, so therefore the area in yellow, which is what we want, as we discussed, it's the area of the red of the curve, which is 9. Take away the area in the triangle under the line, which is 9 over 2. That's 9 over 2. And there we are. So the area in yellow overall is 9 over 2. So yeah, alternatively, you could have just, what we could have done is actually simply, because the blue area is underneath the line, we could have integrated the line. So I'll do it down here, or we could have integrated the line between 0 and 3. The line was actually just y is equal to x, so it'd be x dx, right? So we could have integrated the line alternatively between 0 and 3, between the same limits, to get the blue area as well, because it's underneath the line, right? And you would have got 9 over 2 if you computed this integral, the integral of the line, which is y is equal to x, between the same limits, to get the area under the line, okay? Either or, again, you could take your pick. You could either consider the triangle that is formed, or you could just integrate the line. Either or, the area is 9 over 2. And that's the whole idea, right? The whole idea is to consider splitting up the area into areas under the curve, then areas under the line, okay? And we can separate it to get the area that we want, okay? Alright, okay, so let's have a look at this example. So we are given here a diagram of a sketch with a curve x of x minus 3 and the line y is equal to 2x. We need to find the area of OAC, which is again in yellow, okay, so that area there. Okay, well, again, what are our limits? Well, where's the, in terms of the x values anyway, where are my limits of x? So with the region, so obviously we know that the region starts here when x is 0 and it ends at this intersection point here at B, right? So we need to find the two endpoints first. When we know that 0 is the left limit, but what about the right limit here? It's the point of intersection. So actually, again, we can intersect the curves. So y is equal to 2x, and which is the line, and y is equal to x of x minus 3, which is the curve. So we're going to intersect, we equate them, intersect them to get this intersection point C. Okay. Okay. So they intersect, which is the line and the curve, which means if we equate them, we get 2x is equal to x of x minus 3 if the y values are the same as a result. So then we can expand the bracket to get 2x is x squared, take away 3x. Then we move the 2x to the other side to get x squared, take away 5x equals 0. So x lots of x minus 5 equals 0. So that means x is 0 or x is 5. Well, x is 0 is this intersection point here. We know it's the origin, but x is 5. That must mean that this is 5, right? Here, okay? 5 there, okay? So the intersection point is when x is 5. Okay, so that is my limits then. So again then, I want the area in yellow. So we're going to find that. Well, we obviously can't do it directly, but what we can do is consider the area. We could consider the area under the line is on top of the curve. So we can consider the line. We can consider the area under the line first, right? Okay. And then I'm going to take away the area under the curve. Well, actually, if we consider the area under the line, actually, let me draw this. So if I just exclude the curve, right? If I draw this again, but just with the line, something like that, right? Well, between 0 and 5 and 0. Obviously, the whole area underneath the line is here. I'll do that in blue again. Right. But obviously, we don't just have a line. We have a curve as well. Okay. So I'm going to get rid of this now. I don't need this anymore. So then, if I redraw the graph, but I'm going to add the curve in. So I have the same straight line, right, between 0 and 5. But now I have the curve as well. Something like that, right? So now what's happened is the whole area in blue. Oh, not like that. The area in blue, which I had before with just a straight line, the area under the line, it would be this area, right? But if I consider, but then I have the curve that splits up the area, as you can see, right? So what's happening in it is this blue area is getting split up above and below the curve, right? So what's happening is we've got this area in yellow, but I have this extra area underneath the curve here in red. Right, I hope you can see that, right? So what's happening is the area in blue is now equal to the area in yellow and red. You can spot that, right? The area in blue, which is the whole area under the line. In this case, when we have the curve that splits up the blue area, we've got the area in yellow and the area in red. Okay. Well, the area in red, hopefully you spot. Well, actually, if we can find what's this point here going to be? This area, this point here where the curve crosses the x-axis. We can find that, right? Because if it crosses the x-axis, so remember the curve is this equation here. So if I set x of x minus 3 equal to 0, it crosses the x-axis when x is 0 or x is 3. This is the curve, right? The curve equation. So obviously 0, obviously we can see that, but that would mean this would have to be 3, okay? The root 3 corresponds to this point here, where the curve crosses the x-axis. So what hopefully you can see, this red area is the area under the curve between 3 and 5, right? So again, in summary, the area in yellow, no, the area in blue, sorry. Well, the area in blue is going to be the area in yellow and red combined. But I want the area in yellow. So the area in yellow is going to be area in blue, take away area in red. Okay, so hopefully again that makes sense with the visualization of the areas I'm considering. So in terms of the line and the curve, the area in yellow, the area in blue is the area under the line. But the area under the line between 0 and 5, okay? Take away the area in red, but it would not be between 0 and 5, because if as we discussed, the area in red under the curve, that is between 3 and 5 here, okay? So, very important distinction there, okay? Key detail. So now we're in this point where we can compute the two areas, okay? So the area in blue, first of all, the area under the line here, well, again, spot, we've got a triangle, right? So if we are between, so here, if we're between 0 and 5, well, the base would be 5, but what about the height up here? Okay, well, what would this point be up here, right? So again, the equation of the line is y is equal to 2x. So that means the coordinate, if x is 5, right, x would be 5 up here, y would be 5 times x, 2 times x, which is 2 times 5, which is 10. So the y coordinate would be 10. So here, at the base here, it'd be 5, 0, because obviously it's on the x-axis of y 0. Up here, y is 10, so we've gone up by 10. So that's my height. So therefore, the area in blue, or the area under the line, is the triangle half times base times height. And we discussed, as we've seen here, the base is 5, the height is 10. So it'd be half times 5 times 10. That'd be 50 over 2, which would be 25. Okay, right. So we dealt with that bit. Now the area under the curve, the area in red, which we need to work out next. As we discussed again, it is between 3 and 5. Okay. So area under curve is between 3 and 5. So we're integrating between 3 and 5 of the curve. Now the curve is x of x minus 3. And so at that point we just compute this integral. So that would be, if we expand it, we get x squared, take away 3x dx. And then we can integrate. So that would be that would be x cubed over 3. Take away the 3x would be 3x squared over 2, between 5 and 3. And so at that point we just sub in our limit. So that would be a third of 5 cubed, take away 3 over 2 of 5 squared, take away a third of 3 cubed, sorry, take away 3 over 2 of 3 squared. And so if we put all that in the calculator, we would get we get 26 over 3, okay? So, that's the area under the curve in red, hence the area in yellow, which is what we want. That's going to be the area under the line, which was 25, take away 26 over 3. And so if we work that out, we get 49 over 3. And that is my answer. Okay, cool. So, yes, so it can be quite, especially for the first time, it can be very tricky to visualise the areas you need to work out, but hopefully you start to get an idea now. And actually, maybe you might need to intersect the curves and the line together to get the intersection point. That'll give me my limits, my x values, and so on. And so again, the idea is we can split up the area under the line and the area under the curve. Now, two things. First of all, the area of the triangle, the area under the line, which was again in blue here. Alternatively, you could have just integrated the line between 0 and 5. So you could have done the integral between 0 and 5 of the line 2x dx. If we work that out, you should have got 25, okay? You should get the same area as the triangle because they're the same thing, right? So again, you could integrate. and do that integral. You should get the answer if you're not comfortable with finding the triangle. The second point is, I must emphasize here, we integrated the curve between 3 and 5. If we integrate the curve between 0 and 5 instead, but a is 3 here, well, actually we've got this negative area here, so you can see where the curve between 0 and 3 goes underneath the x-axis. That's not part of the region of 1, okay? So that would be that would affect my answer. It would be wrong. So you need to make sure that it's the area like that kind of is involved, if you get what I mean. So the area here between 3 and 5, the area under the curve in black here, that's still underneath the line. Okay, so we can take that away from each other. The problem is this area under the curve here is not under the line because it's under the x-axis. So yeah, you just need to kind of pay attention to exactly what things look like, right? So yeah, the area under the curve is between 3 and 5 here. Okay, right. Okay, so we've got this question now. So we're given a line with equation y is 10 minus x, and it cuts the curve with y is 2x squared, take away 5x, add 4. Firstly, we need to find the coordinates of A and the coordinates of B, which are here and here. Well, coincidentally, they're both intersections with the curve and the line. So the curve and line intersect. So at that point, we're just going to equate the two together. So y is 10 minus x, that's the line, and y is 2x squared, take away 5x, add 4. So at that point we just solve them, right? Solve them simultaneously. So if I set them equal, that means 10 minus x will be equal to 2x squared, take away 5x, add 4. If I set the y's together. So then I move the left side to the right, so I'm going to get 2x squared, then minus 5x add x. If I add x to both sides, I get minus 4x. Then if I subtract x to 10, if I subtract 10 to both sides, 4 minus 10 is minus 6, equal to 0. So now I need to solve this quadratic, and actually I can just divide by 2 to make it easier. So then I get x squared, take away 2x minus 3 equals 0. And actually I could factorise, hopefully. So two numbers that multiply to get the minus 3, add to get minus 2. Well, they've only factors of 3 and 1. So I could actually get minus 3 and plus 1 as my factors. Because then minus 3 times 1 is minus 3. Minus 3 add 1 is minus 2. That's great. So it factorises x minus 3, x add 1 equal to 0. So x is 3, or x is minus 1. And there we are. So those are my 2 points, but they want the coordinates, right? So that means I need the y values too. So if I'm going to plug these two x values back into y, so y is here, y is 10 minus x. So that means if x is equal to 3, then y would be 10 minus 3, which is 7. And then if x is equal to minus 1, then y will be 10 take away minus 1, that's a double negative, add that to get 11. So therefore, so my points are, my coordinates are either when x is 3, y is 7, or x is minus 1, y is 11. Now which one is A and B? I need to label which one is A and B. Well, A is on the negative, it has a negative x value, and B has a positive x value. Which means out of these 2 points, this has to be A and this has to be B as a result. So therefore A is minus 1, 11, and B is 3, 7. And there we are. And we can also label that as a result. We can label the x values. So minus 1 there and 3 there. Okay, cool, that's part A done. Okay, cool. Then obviously for part B, you can probably guess we need to find the area of the shaded region R. Okay, so again we're going to consider, I'm going to do it down here, the area of R. Well, again, it's complicated because we've got a straight line involved. It cuts the curve off, so the area is a bit cut off, right? So what we can do, hopefully, what you can do is actually, if I just add on these lines, so to indicate clearly the limits, the endpoints, right, between minus 1 and 3. That's what I'm integrating between. So actually, if I consider the whole curve, no, sorry, if I hope you can visualise that to get the area of R, like with the other examples, I could do the area under the whole line, right, because the line is on top. So the area under the whole line, you can see that in blue. And then the area under the curve is in red. That's going to be the area under the curve, right? So hopefully you visualise what I've got left. If I take away the whole blue line, the whole area under the line, take away the area under the curve between red, blue and red, I get just R as a result, okay? So that is how I get my area. So hopefully you get that you can visualise that. You're convinced that's what we do. So the area under the line, take away area under curve. So the area under the line, well, if I get rid of this red stuff now, well, firstly, the area under the line, it's between minus 1 and 3. So, well, at that point, we actually won't get a triangle. If I integrate the whole, if I draw the outside of the, what's it called? If I draw the outside, the perimeter of this, so the line is here between minus one and 3. Then I've got the two endpoints, and then the x-axis. I haven't got a triangle here. I've got a trapezium. So what you could do then is find area to get the area here, the area in the trapezium here. You'd have to find the area of the trapezium. We could do that. But actually, I'm going to show that actually we could alternatively just integrate under the line, and this is where I said that it can be more complicated. We might not get a simple triangle, so you can find the area under the trapezium there. This trapezium, right? Again, as I'll show you here, the area under the trapezium, which is a half times the two parallel sides. If I call that A and B, that would be A plus B times H. That would be the height H. You could do that, but I'm actually I'll show an example where we can integrate under the line, and it actually is a bit more straightforward, okay, in this case. So the area under the line, if we integrate, is simply between minus 1 and 3. So if I integrate between minus 1 and 3, the line has the equation, where was it? 10 minus x dx. So I'll just work out that integral, okay? If you don't want to go down the route of trying to find the trapezium, this is the safer route of just integrating the line between the two endpoints, like with the curve. So then if we integrate this, that'll be 10x, take away x squared over 2, between 3 and minus 1. So then we plug in our endpoints, we get our limit. So we get 10 lots of 3, take away a half lots of 3 squared. Then I'm going to take away, plug in minus 1, 10 lots of minus 1, take away a half lots of minus 1 squared. And so then I've just put that in the calculator. I get I get 36. Okay, so that's the area under the line. Now the area under the curve then, which is again this portion here under the curve, that's going to be between minus 1 and 3. Okay, and the curve is 2x squared minus 5x add 4. And actually, that's quite nice. We don't need to do anything to that. We can just integrate it as it is. So then, if we integrate this, that would be 2x cubed over 3, and then minus 5x squared over 2 add 4x between 3 and minus 1. And so, if we plug in the two limits, well, we're going to get 2/3 of 3 cubed. Take away 5 over 2 lots of 3 squared. Add 4 lots of 3. Then I'm going to take away plug in minus 1. So that'd be 2/3 of minus 1 cubed. Take away 5 over 2 of minus 1 squared. Add 4 lots of minus 1. And so if I put all that in the calculator, I get I get 44 over 3. Therefore, the area I want, the area of the region R, is the area of the line, which was 36. Take away 44 over 3. And so that will get me 64 over 3. And that is the area of R here. Okay. Again, as a final reminder, the area under the line is that whole area, which is actually the trapezium, right? We could find the area of the trapezium, but instead I integrated simply under the line, and I took that whole area here away from the area under the curve, and then that got me the region R. Okay, so there we are. Okay, cool. And again, it's one of these things I always encourage practicing yourself. Again, whether you look at other questions or you pause the video and then you do the questions yourself and see where you get up to, if it matches what I've done and it makes sense. But I really do encourage practicing these questions to help you really visualize the areas you need to work out and take away from one another. Okay, that's the whole area. That's the whole idea. You find the areas under the curve and the line, you take them away from each other to get the desired region that you want. Okay, so we've got this question here. We're told the diagram, we're given a sketch with the equation of the curve x squared add 1 and the line 7 minus x. And actually, they've given us two regions, region 1 and region 2. And actually, the question is to find the both regions. So firstly, region 1, which is in yellow. Okay. Area of region 1. Well, again, the region 1 is between this endpoint and this endpoint here. So the two intersection points. So before I actually work out any areas, I'm going to need to find these two intersection points here and here to get me my limits. Okay, that's where the region is bounded between. So I'm going to intersect them. I'm going to say that the curve and the line intersect. You don't have to write this necessarily, but just making it clear what's going on. So that means y is x squared add 1, which is the curve, and y is 7 minus x. So if I equate them together, that means that 7 minus x is going to be x squared add 1. If I move all that to the left to the right, I'm going to get that x squared add x. Take away 6 equals 0. 1 take away 7 minus 6. Then I can solve it. So I can factorise it perhaps to get so two numbers that multiply to get 6, and add times to get minus 6. Sorry, and add to get 1. Well, actually, the factors of 6 are just 6 and 1. These two don't add or take away to get 1, but 3 and 2 does. That's my desired factor. But actually, I want minus 6, so one of them needs to be negative. Negative 2, because then 3 add negative 2 is plus 1. So, my factors are x plus 3, x minus 2, set to 0. So, x is minus 3, or x is 2. Okay, so again, that's my 2x values. So hopefully it makes sense then that if I go up, that this point at that point in there is going to be -3 because it's in the negative x-axis, -3, and this will be +2. Those corresponded to the two intersection points. So now we should be in a position to work out the area of the region 1. So region 1, which is in yellow here, well, hopefully you notice it's going the curve on top, so it's going to be the area under the line, which is all here, all here, and again we get a trapezium shape there, right, from the perimeter. Hopefully you can see we get a trapezium, the area of the trapezium. Okay, so it's going to be the area under the line, right? You can see here. Take away the area under the curve. And hopefully you can see we're left with just the area of the yellow area of region 1. So the area under the line, take away area under curve. And again, I'm just going to integrate the line firstly to find the area under the line. If I get another trapezium, I'll work out the trapezium to give an alternative way of working things out. But the area under the line, well, the area under the line here, well, it's just the integral between -3 and 2 of the line. And the line is 7 minus x. So we just integrate that. So that would be, if I integrate it, that'd be 7x, take away x squared over 2, between 2 and -3. So then we sub our limits in. So that'd be 7 lots of 2, take away a half lots of 2 squared, then take away then I plug in -3. So it'd be 7 lots of -3, take away a half lots of -3 squared. Then I just put all that in the calculator. And I get 75 over 2. So that's the area under the line. Then the area under the curve. So again, the curve here in the same space. That's this region here between -3 and 2. It's the area between -3 and 2, right, of the curve. And the curve was x squared at 1. Okay. Pretty nice curve to integrate actually. So then if we integrate that, what x squared goes to x cubed over 3, and 1 goes to just 1x, or just x, okay, between 2 and -3. So now if we sub our limits in, that'd be a third of 2 cubed, take plus 2, take away then a third of -3 cubed, take away add -3, so -3. Put all that in the calculator, we get $50 over 3. Therefore, the area of the yellow region, the area of region 1 in yellow, is the area under the line, as we discussed, 75 over 2. Take away 50 over 3, the area under the curve. If we work that out, we get 125 over 6, and that will get me the yellow region here, the area beneath the curve, and the area between the line and the curve there. Right, okay. Then the area of region 2. So I'm going to get rid of the lines. So between -3 and 2. Okay, so the area of region 2. What you can spot here is, if I split this up, right, if I do that line here, well, actually region 2 is basically a composition of the area under the curve here between 0 and 2, then this region here, which is the line between 2 and 7. Okay, so essentially what's happening here is the area, we can split that up then. The area of region 2 is the area under the curve, firstly, but again, if I make it clear, so that's 2 there. So the area under the curve, but only between 0 to 2, okay? From 0 to 2. And then I'm going to add on, then after 2 to 7, then it's the area under the line here. You can see that, right? So that's the line 7 minus x. So the area under the line from 2 to 7. Okay, so the area under the curve, firstly, strictly from 0 to 2, so we're integrating from 0 to 2, the curve is x squared add 1, right? Dx. So I should make it clear. Firstly, the area under the curve, that's what I'm working out first. So it's this integral here between 0 and 2. Well, actually, we already integrated it, but in part A, you could just copy. It was this x cubed over 3 add x. So it'd be x cubed add 3 over x between 2 and 0. So now we plug in these limits. So it'd be a third of 2 cubed add 2, take away a third of 0 cubed add 0. So if we work that out, I get 14 over 3. Okay. Right, so that's the area under the curve. And then the area under the line, specifically from 2 to 0, 2 to 7, sorry. Area under line. Well, we can integrate the line from 2 to 7, right? Those are my limits. Here, right? This region from 2 to 7. The line is 7 minus x. From 2 to 7. And so if I integrate that, that would be 7x minus x squared over 2 between 7 and 2. So if we work that out, that would be 7 lots of 7. Take away a half of 7 squared. And then plug in 2. That would be 7 lots of 2. Take away a half of 2 squared. And so if I work that out, I get 25 over 2. Therefore, the area of region 2 is these added together, as we discussed. So that'd be 14 over 3. Add this 25 over 2. So if I do that, I get 103 over 6. And that is my area of region 2. Which is in blue here. Okay, so hopefully you could visualise what's going on there. I guess the hardest bit is visualising the areas that need to work out, but hopefully that made sense. Okay, so let's have a look at some exam questions then on this. Okay, so we've got this question first. So before we do any integration, we've got this quadratic and we're told to basically complete the square, right? You should recognise this is completed square form because it's just a single bracket of x all squared, right? That is a completed square form. Again, remember you need to remember earlier parts of the course because questions might link multiple topics together. So if we complete the square on minus 3x squared add 12x add 8. Well, my first process is to factor a minus 3 out. So then I factor minus 3 to get x squared. Then 12, if I divide that by minus 3, I get minus 4. So then minus 4x. And actually, I can just leave the 8 outside, the number outside. That doesn't impact by completing the square. So then I can complete the square in the middle here, so -3. Then that would be x, and then half of -4 is -2 all squared. Take away, then -2 all squared, that's +4. So take away 4 plus 8. Then I'll just expand it to get -3. Lots of x -2 squared. -3 times -4 is +12 plus 8. That would be +20. And that is my answer for part A. Cool. Then part B says the curve, which is again the quadratic, has a maximum turning point. You can see that here, the maximum turning point. Well, we complete the square, so the maximum turning point, we can read off the fact that when we complete the square, the turning point is when the bracket's set to 0. So x -2 equals 0, which means x has to be 2 at the turning point. And then what we got left is if this is set to 0, the bracket, we just get 20. So y would equal 20. So therefore my turning point, or m, the coordinate m is x is 2, y is 20. And that's quite a nice 5 marks, that is. There we are. Right, so I can label that here actually, 220 for m. I might need that, most likely. They didn't ask you to work that out for no reason, most likely. So, now to get to the integration part. So, we are given a sketch of the curve C, and the line L, you can see here. The line L passes through M and is parallel to the x-axis. The region R is bounded by C, L on the y-axis. You can see region here. We need to find the area. Okay. Right, how are we going to find the area here? Well, again, it's a similar sort of idea as we've just seen. Actually, the region is between the line and the curve. So actually, we know M here. We know X is 2. Right, so actually the area of R, if I think about it, it's going to be the whole area under the line L, right? You can see here L, so it's going to be this whole region under the line, or area under the line. And then I'm going to take that away. If you think about it, the whole area, I'm going to take away from the area under the curve between 0 and 2, right? Hopefully you can see that. The area under the curve, okay? Right. So firstly, the area of the line, let me work that out, the area under the line. So, the area under the line, again, if I show you that in blue, the area of R included with the area under the curve, right, between 0 and 2. Actually, notice if I then draw the perimeter line, in blue, the perimeter, actually, we get a rectangle. So what we can do is actually just work out the area of the rectangle, right? So the area of the rectangle then, there we are. So the area of the rectangle, firstly, this width is 2, right, from 0 to 2, it's 2. Then what about the height of it, right? Well, actually, we know that y is 0 at the bottom here, and then actually at M here, y is 20. So we've gone from 0 to 20, so the width, the height is 20. Therefore, the area of the rectangle is simply going to be 2 times 20, which is 40. So that'll get me the area under the line. Okay. Alternatively, if we didn't spot that was a rectangle, right, between the line and the axis, if we didn't, if I get rid of all this, if you didn't spot that, well, actually, you could still integrate the line, right? Integration is still possible, because actually the line, what's the equation? It's a flat line, so that means y is equal to 20. Okay, y is 20 because obviously that's when m is 20. Well, if y is equal to 20, what you could simply do is integrate the line, which is the integral of just 20 dx, right, between x is 0 and x is 2. Well, actually 20 is quite easy. That'll just go to 20x, right, between 2 and 0. If you then work that out, if you substitute 2 and 0 in, 2 and 0, you should get 40 out of that, okay? So either way, you could either spot it was a rectangle, that simply the area under the line, right, in this way, or you could simply integrate the line from 0 to 2, right? It might look a bit weird because y is just a number because it's a flat line, but you can still integrate that because 20 is a constant. We just add an x on if we integrate it. As you can see here, 20x is the integral of 20. Anyway, so that's the area of the line. Now then, the area under the curve hopefully should be a bit more straightforward. So then, if the area under the curve here, well, that's going to be the integral. The curve is between 0 and 2 here. So we're integrating. So we're integrating from 0 to 2 of the curve. Now the curve, we're told, is minus 3x squared at 12x. Add 8. So then we just integrate that. So if we do that, well, if we integrate that, that would be minus 3x cubed divided by 3. Then 12x will go to 12x squared divided by 2. Then 8 goes to 8x. Between 2 and 0, and actually then we can simplify the fractions because minus 3 over 3 goes to minus 1, minus x cubed then 12 over 2 goes to 6, so 6x squared, add 8x between 2 and 0. Then we just plug in our limits, so that would be minus 2 cubed, add 6 lots of 2 squared, add 8 lots of 2, take away minus 0 cubed, add 6 lots of 0 squared, add 8 lots of 0. Okay. And so if I work that out, put that in the calculator, I get 32. Okay. And by the way, you might be asking, why you should bother writing this down if it all goes to 0? You still have to show you're working, even if it's redundant. You need to show explicitly that you're substituting the two limits in. Okay, but there we are. Goes to 32. So therefore, the area of the region which we're interested in, that's going to be the area under the line, which was 40. Take away 32 to get 8. So that leaves me with the region R there. Okay. So again, hopefully you can visualize how I found the two areas there, right? And again, so just to be clear, so the area under the curve, if I did that in yellow, the area under the line, sorry, from 0 to 2. Actually, let's do a different color. Was this whole area here, which obviously gets me my rectangle. And then if I take that away from the area under the curve, which is here, take that away, I'll just get the area of R. Okay, so I did the area under the line between 0 and 2, take away the area under the curve from 0 to 2. There we are. Okay, let's turn that back. There we are. Okay, final exam question. Here we are. Okay, so we're given a sketch of a curve again. This curve here. And we're told that the line L here is a tangent to the curve at P. So actually the first part of the question is we need to show that the equation of the line has that equation there. Okay. So that is actually nothing to do with integration, that's differentiation, because it's all to do with tangents, okay? So, okay, so y is a third x squared at minus 2 root x add 3. The tangent is dealing with the gradient at the point, so we need the gradient, so we're going to need to differentiate. But this root x needs to be a power before I differentiate. So that'd be a third x squared minus 2x to a half, add 3. Right, so now we can differentiate. So dy dx, that'd be, well, again, we times the power in front. So that'd be 2 times a third, which would be 2/3. X, and knock 1 off the power. X to the 1, that's just x. Then minus 2x to a half, the half comes to the front. So 2 times a half is minus 1. So minus x to a half, and minus a half if we subtract 1. Then 3, as that's a number, that just goes to 0. So that is my gradient. Right, so the gradient at P then, at P here, well, we need to substitute an x in. We're told at P, x, at the x coordinate is 4. So, at x is equal to 4, dy dx, if I plug 4 into here, I get 2/3 of 4, take away 4 to the minus a half. And so if I do that, I get 13/6. And so therefore the gradient is the same as the tangent gradient. So that means the gradient of the tangent is 13/6. Again, we looked at that when we looked at tangents in the differentiation chapter. Okay, so then the line of the tangent, so obviously any line is y is mx plus c. We know that m, the gradient, is 13/6. So y is 13/6x at c. So now we just need to find c. But again, we know that p by itself, p is on the line, the tangent, right? Okay, but we only know what the x coordinate is. We know that p is equal to x is 4, y is just y. We don't know what y is. But y, we actually do know what y is. It's this equation here. So I'm going to sub x is 4 into the line, into the curve. So into y, which is a third x squared, at 2 root x plus 3. Minus 2 root x plus 3. So if I do that, then I get that y is going to be a third of 4 squared. Take away 2 root 4, add 3. If I work that out, I get y to be 13/3. That means my point P is 4, x is 4, y is 13/3. So now we can sub that point into the tangent to get C. So sub P, I'm going to sub 4 13/3 into the tangent. So therefore y is 13/3. It's going to be 13/6, lots of 4 for x, add C. And okay, so that means 13/3 going to be, well, 13/6 times 4 is 26/3. Add C. And so simply then, to get C, we're going to subtract 26/3 to both sides. So 13/3, take away 26/3, I get minus 13/3. So therefore, y is going to equal 13/6x minus 13/3. So that's my tangent, but it wants it in this particular form. So what I need to do is simply rearrange. Okay, so firstly I note that every term is on the left equal to 0. So I'm going to need to move everything to one side. So that means I'm going to get minus 13/6x, add y, add 13/3 equal to 0. Then I'm going to get rid of the fractions. So I'm actually going to times everything by 6, because then that'll get rid of the whole fractions. So minus 13/6 times 6 is minus 13x. And then add 6y. And then add, well, 13/3 times 6 is 26 equal to 0. Is that the form they want it in? Very, very nearly. We need to actually switch the signs. We need to divide by minus 1 to get positive 13x. So then if I times by minus 1, I get 13x minus 6y minus 26 equal to 0. And that is what they got. Cool. There we are. That's part A done. Part B, the integration part now. So, we are told now, basically we're told to find the region R. They've shown the region for us right here. So how are we going to work out that region R? Well, let's think about it again. Well, actually, if the region R, you can't really see it beyond this point, but actually the region R goes up to P. There, very faintly. So actually the two endpoints of the region are between 0, the origin, and P. But P, we saw that X is 4, okay? X is 4 at P. So we're integrating from 0 to 4. Okay, so what exactly are we integrating then? Well, again, visualise then that to get the area of R, we're going to get the area under the curve between 0 and 4, which is here. That's the whole area there. So the area of R, which is the area under the curve between 0 and 4. From 0 to 4. Okay, but obviously I'm going to have to take away. Well, actually then, the area under the curve, or here, I need to get rid of this area after the line here, right? I need to get rid of that to get to leave me with R. Well, then we're going to take away to get this area here. It's going to be underneath the line, right? Now it would be between 0 and 4 because obviously that's the point. Well, that's my limit here from the line. So the line is between this point here and 4. How do we get to that point there? Well, it's a route, right? It's where it crosses the x-axis, the line does. Well, we just worked out the line in part A, right? So we need to, okay, well, 13x, I'm going to work it up. I'll work it up here, actually. So to work out where the line, so again, the line is 13x, take away 6y, minus 26 equals 0. If we want to find where the line crosses the x-axis, that's when y is equal to 0. I need to set y to 0, right? So if y is 0, then that means we get 13x, take away 6 lots of 0, take away 26 is equal to 0. So 13x equals 26. Therefore, x is 2, right? So that means it's 2 here. Okay, hopefully you're clear with that, right? All I did was find the x, right, the root, right, when the line, the tangent line crosses the x-axis, which you need to remember because it's on the x-axis, y is 0. So I set the line, I set y to 0 to find x, and that gives me 2, which is where it crosses there. So hopefully you can see then that the area under the line, I've marked here, that whole region is between 2 and 4. So that should leave me the area of R. So then if I take that away from the area under the line, from 2 to 4. So at that point, it's just a series of integrations, really. So firstly, the area under the curve. Well, as we discussed, it's between 0 to 4. And then the curve has this equation here. A third x squared, take away 2 root x, plus 3 dx. Well, if we're going to integrate, but firstly, this root x is going to be a bit of a problem. I'm going to need this root x here. I need to convert that to a power. So that's the same as 4 to 0 of a third x squared, take away 2x to a half, add 3 dx. Okay, cool. Now we can integrate everything. So if we integrate that, that would be, well, a third x squared will go to a third x cubed, then divide by 3. And then 2x to a half, that'd be 2x. If we add 1 to a half, that'd be 3 over 2. Then divide by 3 over 2. And then 3 goes to 3x between 4 and 0. We can clean up the whole fraction mess we've got inside first. So a third divided by 3 is a ninth. So we get a ninth x cubed. Then minus 2 divided by 3 over 2 is minus 4 over 3. X to the 3 over 2, add 3x. Okay, so it's a lot cleaner now. Now we can plug in our limits. So then if we plug in 4, we get a ninth of 4 cubed, take away 4/3 of 4 to the 3 over 2, add 3 lots of 4. Then I'm going to plug in 0, so a ninth of 0 cubed, minus 4/3 of 0 to the 3 over 2, add 3 lots of 0. So if I put that in a calculator, I get 76 over 9. Okay, so that's the area of the curve. So then the area under the line, as we saw here, it's from 2 to 4, right? And then the line, well, the line they told us was this. Well, we'll need to rearrange to get in terms of y. But actually, we don't need to do that because we did that already. It's this. This is the equation of the tangent originally. So that is y. So we can sub that in. So that it'd be 13 over 6 x. Take away 13 over 3 dx. And now we can just integrate that, right? So if we integrate that, okay, well that'll be 13 over 6x squared, then divide by 2, and then 13 over 3x. And that'd be between 4 and 2. And then again we can tidy up the fraction just a little bit, because 13 over 6, divide that by 2, I get 13 over 12. X squared, take away 13 over 3x, between 4 and 2. Okay, so then if I plug in 4, that'd be 13 over 12, 4 squared, take away 13 over 3 of 4, take away then 13 over 12 of 2 squared, take away 13 over 3 of 2. Okay, so then if I work that out, I get 13 over 3. Cool. So therefore the overall region R, the area of the region we want, again as we discussed, it was the area under the curve, take away the area under the line. Well, the area under the curve was 76 over 9. So 76 over 9, take away 13 over 3. And then if we work that out, we get 37 over 9. And that is my area of R. Okay, fairly tricky. I thought that slightly tricky that was, especially to work out visualize the area that we needed to find. But hopefully it made sense of how we split it up, the region R, right, between 0 and 4, as the area under the whole curve, firstly, and then I take away from the area of I'm taking away from the area under the line from 2 to 4 there. Okay, and that leaves me the region R. Okay, so that is integration. So hopefully you can start to visualize basically how to take away areas under curves from areas under lines. Okay, and yeah, so that I'll see you next time.